modular transformation of the Mach theta functions alone. So what Zweger showed is that, well, here is an example under the two generators of SL2, this vector H, which is a difference between the Mach vector and the non-holomorphic vector, transforms as a vector value the way to happen. So this is on one hand very nice, because we now have fully understood the way in which these functions fit into the theory. By the way, something is true for all of the other Mach theta functions as well. But on the other hand, we've lost the holomorphic properties of these Mach theta functions. However, it was a really exciting time because right around the same time when Zweger was writing his thesis and working out these transformation properties of Mach theta functions, other mathematicians, so Jan Brunier and Stoka, were studying what are called harmonic Maass forms for a totally different reason. And it turns out that Zweger's work and these harmonic Maass forms are very related. So what are harmonic Maass forms? So just like modular forms, they come equipped with a weight. And again, the weight can be an integer or a half integer. We have some level. I'll formally define gamma 0 for n on the next slide. This is a certain congruent subgroup of SL2Z. These functions need to be smooth, and they should satisfy three properties. One, they need to satisfy some appropriate transformation law on this particular subgroup of SL2Z. And what you see here in brackets, the function transforms in a simple way if we have an integer weight, and then it transforms in a slightly more complicated way if we have a true half integer weight. This transformation in the first piece of my transformation law here is just in accordance with the theory of ordinary half integer weight modular forms. I'll define these symbols that show up in the half integer weight transformation on the next slide. They are basically plus, minus 1, or I. Secondly, well, these functions are called harmonic. Why are they harmonic? Because they're annihilated by a Laplacian operator. This is some degree 2 differential operator that's defined here in terms of the real and imaginary parts of tau x and y. So this function should be killed by this operator. And like ordinary modular forms, they should satisfy some appropriate growth condition in the cusps. I'll explain what that means in another couple of slides. So just remember three things. It should satisfy some appropriate transformation law. It should be harmonic, annihilated by this operator. And it has to satisfy an appropriate growth condition. So let me tell you a few more technical ingredients. Here's gamma 0n, this congruent subgroup of SL2, where the lower left entry should be congruent to 0 mod n. If we have a true half integer weight, for technical reasons we require 4 to divide n. We're using the Kronecker symbol, the Joner symbol. This is plus or minus 1. And that shows up in the half integer weight transformation law. And this number epsilon, where d comes from the matrix ABCD, so it's either 1 or I, depending on what d is modular. There's some technical remarks about the transformation law. Okay, if you're worried about taking square roots, you can always take the principal branch. The growth condition, okay, we say that we allow linear exponential growth in the cusps. By that we mean, well, this function has some polynomial in 1 over q. Doesn't behave so well. But if you subtract off that polynomial, the function grows like e to the minus epsilon y. For some epsilon that's positive, as the imaginary part of tau y goes to infinity. So a condition like this we refer to in words as linear exponential growth. So what can I tell you about their Fourier expansions, you may be wondering. Modular forms have Fourier expansions. Harmonic Maass forms have expansions. And it's actually not too difficult a lemma to prove, just using the definition, that harmonic Maass forms decompose into 2 pieces. A holomorphic part, so this is a nice Q expansion. It's a holomorphic Q expansion. Okay, maybe it's meromorphic. Maybe you start at a negative integer, but you start with a nice Q series at some integer. This resembles the Fourier expansion for ordinary modular forms, but there's more. Think of our example, due to Zweigers with the Mach theta functions. There's some nice Q expansion, and then something that is not holomorphic, that need to be added. So the non-holomorphic parts, here I've written them down as sums over all negative integers. So q to the n. Now we're summing over negative powers q to the n. For some coefficients, and then multiplied by some incomplete gamma function. And you see there that this incomplete gamma function takes as one of its parameters the imaginary part tau. This is not holomorphic. So all harmonic Maass forms decompose into 2 pieces like this. Example, Ramanujan's Mach theta functions are holomorphic parts of harmonic Maass forms. So here is a holomorphic part, again needed to multiply by this appropriate power of q. It's Mach theta gamma. And because these Mach theta functions are Ramanujan, are some of our first concrete examples of holomorphic parts of harmonic Maass forms, Zagier officially defined a Mach modular form in general to be any holomorphic part of a harmonic Maass form. So we now have Mach theta functions as examples of holomorphic parts of harmonic Maass forms. And in general, we call those holomorphic parts Mach modular forms. So, in the last 10 or 15 years, there have been many advances in the subject of Mach modular forms and harmonic Maass forms. Many advances in the subject in and of itself, and many applications to other areas. So I've written down just a list of some of the different areas in which we've seen advances in applications, thanks to the development of the theory of harmonic Maass forms and Mach modular forms. And I want to tell you a bit about quantum modular forms. And because I'm going to tell you a bit about some results in quantum modular forms, I'm again going to come back to the combinatorial interpretation and application. So again, remember this picture. We're going to be talking about functions on the upper half plane, or perhaps in the cusps on the boundary, rational numbers, or in the unit disk, or perhaps on the boundary at roots of unity. So here is a modular transformation law. You have some function that transforms like a modular form. It should satisfy a transformation law, as you see here on the middle of the slide. But I want to shuffle that around a little bit, actually. And let me just subtract and divide and rewrite that transformation law as a difference equaling 0. It's another way to think about it. So modular means you transform in the right way with respect to the action of SL2 on the upper half plane. So tau is in the upper half plane. Quantum modular forms ask the question, well, what can you say if you look at such a transformation not on the upper half plane, but on the rationals, on the boundary, and the cusps? Is there anything that can be said? Are there functions that satisfy this property? What does this even mean? Does it make sense? So quantum modular forms are something like modular with respect to Q, not the upper half. There's a question mark here on the right-hand side. It doesn't make sense to put a 0. But what does make sense is to ask that that error to modularity, that difference, is well behaved in terms of its analytic properties. So this is a relatively new definition due to Zagier. So quantum modular forms have some weight, and they map from the rationals to the complex plane, or maybe the rationals minus some discrete subset, that's all right. Such that under SL2, this difference, it's not 0, but it's some nice analytic function in R, some real analytic function, maybe some nice continuous function in R. And I'm not trying to be vague here in my definition. Zagier's original definition was more or less identical to what I've written here in the slide. Sort of the niceness that this difference should satisfy is somewhat flexible. Some of the original examples Zagier wrote down were of continuous errors to modularity, so to speak, in R, or analytic, smooth. I mean, they all satisfy a slightly different flavor of a nice property. So here's one of Zagier's original examples. And this came from a function due to Kontsevich. This function is defined using the Q-Pockemer symbol for rationals, and only for rationals. It converges for no open subset in C, but for any rational number. It's a quick exercise you can work out later today. It's very easy to see convergence for any rational. This was originally studied by Kontsevich for other reasons, but Zagier put this function into the framework of quantum modular forms. It transforms correctly under SL2, and the sort of error to modularity is a real analytic function, except at 0. And it turns out that this function is related to another combinatorial function for unimodal encoding information about ranks of strongly unimodal sequences. So I'm running out of time, so I won't get into too many of the technical details. This is almost like and if one forms a rank with respect to these partition-like numbers, you can keep track of these ranks in a 2-variable generating function, which when specialized will give you some weighted rank function, as in the second line of this slide. So this is another 2-hypergeometric combinatorial function. It was proved by Bryson, Ono, Pittman, and Rhodes fairly recently that Zagier's quantum modular strange function from Kontsevich is equal to the unimodal function under the change of variable x goes to -y. So another combinatorial interpretation of a quantum modular form. But this interpretation allowed Bryson, Ono, Pittman, and Rhodes to extend the modular properties of this function to the upper half plane. Not only does it transform in a nice way with respect to Q, but also on the upper half plane. This is an example of a function that is Mach and quantum at the same time. So in my last couple minutes, I want to return to Ramanujan's claim and tie all of these things together. So with unknown roads, we went back and looked at Ramanujan's claim that the Summer difference between the Mach theta function f and this modular form b should be bounded at roots of unity, even ordered roots of unity. F converges at odd ordered roots of unity, by the way, if you're wondering. So the first thing we did was look on a computer at what happens to these functions at the simplest even ordered root of unity, -1. This was just a couple years ago. Well, as q radially approaches -1, okay, it's exploding as we expected. Great. And now we add the modular form b, and numerically we were observing what we should according to Ramanujan's claim. That sum appears to be bounded by the number 4. We looked at I, and this time the difference appeared to be bounded and radially approaching 4I. So we sought to understand, really, can we say something about these constants? What are they? What's really going on here? We have this relationship, the suggested relationship between Mach and modular forms. We were able to prove a closed formula for the right-hand side of Ramanujan's claim, that it's not so simple. Seeing 4 and 4I, we thought things might be simple. It's 4 times the root of unity or something. But it turns out that in general we get a polynomial in the root of unity, an exact polynomial given here on the right-hand side. Which may look familiar, may or may not. Well, it turns out to be a special case of a more general theorem that we prove using 3 two-variable combinatorial modular and Mach modular and quantum modular forms. So if we fix one argument of these functions to be a fixed root of unity and let q approach another, we end up that this radial limit is a special value of the unimodal rank generating function. So what are we saying? In terms of Mach and quantum and ordinary modular forms, our theorem is saying this. As q tends radially towards a root of unity, the difference between a Mach theta function and a modular form is a quantum modular form, a special value of the quantum modular form. Or combinatorially, you can interpret a theorem in the following way, that the difference between the rank and crank function asymptotically as q approaches singularities is a special value of a unimodal function. So I want to end with 2 things. Later today, or this week, if you have some downtime, you might want to take a look at this nice short expository article by Andrews and Berndt. They took a poll. They polled mathematicians what their favorite things from Ramanujan's lost notebook were. And interestingly, we were able to incorporate 4 of the 5 favorite topics of Ramanujan's works in our one theorem, connecting quantum, Mach, modular, and combinatorial series. Ranks, Mach theta functions, cranks, and some predecessor to quantum modular forms. This is a topic that has continued to be of interest really since Zagier wrote the definition down in 2010. And many, many authors, some of which will meet later this week at the conference, have gone on to further investigate relationships between Mach and quantum modular forms, among other things. So I'll stop here. Thanks very much.